Good morning, everyone, and welcome to our first NetLab series that we're hopefully going to do this on a monthly basis. My name is Eric Marsky, and I'm the Manager of Strategic Partner Development here at ESTEEM. The Web Lab series that Dan did a couple weeks ago, this is kind of a continuation. This is actually going to be more of the technical side of what we want to get out to our customers. And the application that I have for you today is actually on what considerations do we need to make when we're looking at designing a radio system, the RF system as a whole. Um, those that aren't familiar with who we are and what we do, let's go ahead and give a little history, really. The company of ESTEEM was actually established back in 1982. We basically exclusively design and implement wireless systems for well over 38 years now. And we are the manufacturer. We design, do our own IP. We the ownership of the IP and the life cycle. And that is a key element to being able to provide a forward-looking solution into the wireless world, because we have the ability to set when and which level of radio do we want to be able to talk forward and back to within our system. All of our radios are all designed and manufactured here in the US, actually in Washington State. And quite honestly, we have one of the most industry's complete and comprehensive portfolios as far as wireless devices are concerned. We have both licensed frequencies in the 150 to 217, 150, and all the way up to 4.9 gigahertz band. We also have unlicensed frequencies in the 900, 24, and 58. That's what people are kind of familiar with, is the unlicensed band, but we can make many different applications depending upon which system they go into. To date, we have over 45,000 of our radios in service worldwide. The applications that we primarily go into kind of fall within systems that generally are either long distance, very inaccessible, very difficult to get to, or something that may be just a mobile environment. Those kind of fall into water, wastewater, oil and gas, mining, material handling, power and energy, agriculture, infrastructure, and factory floor. Dan did a great job a couple weeks ago, and the last webinar really covered which frequency is best for your application. In other words, looking at all the different parameters available to you, which frequency would go best. So what I want to do is kind of continue on with that series and take a look at what does it take to make a successful radio system. Okay. What we're looking at here is it's actually 3 individual steps. The first step is actually the RF design program, and that's actually what we're going to go over today. This gives us the ability to do a math model analysis of the equipment that we're putting in. Once that's actually completed and everything looks good, like what we want it to do, we actually go out and do a physical test at the site itself. Really, it does is it allows us to not only verify the equipment that we've selected on the first one, but it also gives us the ability to adjust the radio network if necessary for things that don't show up in the math model system. Trees, overhead power lines, buildings, new construction, things like this that we can make modification. As a matter of fact, that's going to be a future net lab here in a couple of weeks. We'll be going over exactly how to do the site survey. And the last and final step to completing a radio system is actually what we do called site commissioning. What we do is we go in after the equipment is installed and actually perform the exact same tests we do on the radio site survey. Now, this may seem like a lot of different steps to go through to actually get a reliable system in, but we need to understand what we're building here. We're building a backbone for all the devices that are going to go onto this network. The network, quite honestly, is no more reliable than it's designed. So a way to look at this is that any unreliable link, any device that's actually attached to that unreliable link will also be unreliable. So we want to make sure we build this as solid as we possibly can do. A difficult aspect that people don't understand is that each radio application, every single system that we build is unique. Now, you may take one from a room that we're sitting in here and move it to the next room over, and it's probably going to work the same way. But understanding that the design considerations, the reflections, the noise, the signal strengths, all of these are going to change as this system moves or in each and every new location. So we need to review how a system is designed each and every time. So how do we do this? Well, the way that we start with is what we call the RF design program. It's a program that we've put together. It's a Microsoft Excel template that allows you to do path loss calculations and will give you some of these warnings. Really what it's doing though, it's telling us, answering a very simple question. Does the wireless equipment that I've selected provide enough signal and bandwidth for the application I'm putting it into? It gives us the ability to find out, is this going to work exactly as we expect it to do? So what I mean by this path loss calculation is, as a radio sends its electromagnetic energy into the air, okay, does it have enough signal to get to the opposite side to be able to provide us with enough throughput to be able to work with the type of hardware we're doing? For example, a very high bandwidth system, say a camera system, is going to require a lot more throughput than, say, just a simple data collection system. So we need to actually analyze that in quite detail to make sure that each and every link within that system is going to be able to provide what we expect it to do. A nice feature about this RF design program is, quite honestly, it's a conservative model. We have to assume everything that happens in that wireless application is going to be a negative result. In other words, every potential loss we have is going to come into the system. So what happens in most cases is that, quite honestly, the installed hardware is generally a much higher signal strength than we actually do from the calculation. So that helps us out quite a bit. The beautiful part of this is it also allows us to modify systems prior to them being installed. So if we find that a particular link doesn't have enough signal strength or isn't going to give us enough bandwidth, we can adjust the equipment for that application before it actually even goes in install. Anybody that's done any kind of radio work, we realize that this is going to be where it's the most expensive, is taking something out and replacing it or making modifications to the system. So it's a huge benefit. So what do we need to know? That's really what we're here to get in this net lab. Is it's going to be very difficult. There's quite a bit of detailed information we get to, but this gives us an idea of how do we start? What do we go with? So what information do I need? Well, quite honestly, it's not that bad. The first thing we need to understand is what radio and frequency of operation are we going to be working with. That's really kind of the focus of what our first webinar was based upon. It's really application based. How much speed do you need? How much is going to then push to which radio we go into? What kind of distance? What application? What environment? All of these different factors are going to push us towards one frequency or one radio versus another. And that's something that we'll be glad to help you work through here at ESTEEM. That's something that we do day in and day out. So we want to make sure that you're comfortable with understanding that. But once we have this root radio, now we can then say, okay, now I've selected the radio. I'm going to start putting pieces of hardware to it. What else do I need to know? The nice part is that we really only need to know two major things: distance and height. Now, distance can be actually gathered by many different sources, quite honestly. We can look at a network map. We can create, really what we're doing is we're going to create a very simple network diagram and just put the distances on it. Now, we can get it based upon maps, GPS, and what you're going to find is any kind of RF design work, one of the greatest friends we have really is Google Earth. It allows us to actually do a visualization of the site we're going to, so we know it's exactly where it's at. Gives us the height, elevation, and one of the nice features is they've added the ability to look at a side profile. And once we've established that, we also need to look at what height is necessary at each of those locations to gain a line of sight. A line of sight is a clear pathway between two antennas. Now, that can be difficult in different situations, but quite honestly, from an RF design standpoint, we can only calculate based upon a line of sight link. It doesn't necessarily mean the system won't work if they don't have line of sight. It's just a very simple thing that we can't make any reliable calculations if the two antennas do not have a clear line of sight. If they don't, the only option at that point is to actually test them. Okay? So as I mentioned to you before, what are the ways of doing this? Well, The nice part about Google Earth is it really gets you several different things. It gets you very accurate site locations because you can visually see them from a top-down view. So if you're looking at a water tank, you can place it right on the top of the water tank. It also gives you the longitude and latitude for each of these locations and distance between them. The biggest benefit to it, quite honestly, is once you establish several different points, it allows you to do kind of a side profile. So you can actually see, as you can see here on this diagram, you can actually see a side profile between the 2 points to see any hills that are in between, a rise in elevation, whatever is between those two. It's a very, very, very powerful tool. Once we've then established it, we can then just start with a very basic network diagram. So what we're going to use for this particular example is we've actually got a 5-site diagram. We've got a control room topping out to 3 different pump sites, and we've got a water tank that's going to be sitting on the top of a hill that we're going to use as a repeater out to pump site number 3. Because the only way to get to that, there is no line of sight between any of the other sites out to pump site number 3. So what we're going to do is take a look at what information do we need to gather and what do we base this upon. Okay, there we go. Okay, so when we're talking about height, what we're talking about here is we're talking about 2 different heights: the terrain height above sea level, and then the height above that to actually gain us that line of sight. So it's actually going to be where the antenna is going to actually be the height. Now, the thing to understand about this, though, is the fact that if you, in many different applications you go into, you're going to be dealing with height above sea level. So if you're sitting at 500 feet, that does not mean that that particular site is 500 feet in the air. So what we need to do first is, now that we've established all the points within the system and we have all the site elevations, what we simply do is we basically compare all the sites to each other. And it's a very simple calculation. All you do is you take the lowest site, as we see here on here, for the elevation differential. We set the lowest site to 0. We then add to that each of those sites the antenna height requirement to gain line of sight, and that then creates what we call adjusted antenna height. And we just simply do that for each one of the sites within the system. As you can see here now, that what we've now got is the adjusted antenna height. We've got our feed line lengths, and then we also can get a basic idea of which type of antennas we're going to need. So sites that are going to talk out to more than one location are going to need an omnidirectional antennas, and sites that only talk into one location, we tend to put a directional antenna to. It really helps in 2 different ways. It not only increases the amount of signal strength between locations, but it helps also isolate the radio system into a smaller location. So what we can do then is, let's go ahead then, what does this RF design tool tell me? Okay, what are we getting out of it? The biggest thing it does is it tells us what we can expect as far as an RF signal level. Okay, what it's actually doing is calculating what's called an ERP, or an effective radiated power. And it takes the power of the radio, takes the losses in the cable, adds to that the gains of the antenna. So we know how much energy is being radiated from a particular location. This program then calculates the path loss over a distance based upon the frequency of operation. We now know how much signal is going to arrive at the remote site. Then we can then base that and look and see how much we can expect as far as RF throughput. This gets very complicated, and the reason this program is very beneficial is because a lot of our radio systems now have variable data rates based upon how much signal strength they have. The more signal they have, the faster they can go. So this actually calculates all of these different variables all at one time. The next thing it also shows you some of the warning signs that we need to be concerned with. Fresnel Zone blockages, blockages due to the Earth's surface. And that may be a term that you've never heard before, so let me kind of give you an idea of what I'm talking about here. Is that if we take a look at, let's just take a look at this very first simple link from the control room out to pump site number 1. We know the control room has 100 feet of adjusted antenna height. Pump site number 1 has 110. The feed line length, the reason that we put this in here is that very much can be a variable based upon the radio that we go into. Say, for example, our Horizon radios, they can actually be mounted directly outdoors, So the cable length is almost inconsequential because that's actually based upon Ethernet. If it's, say, a licensed radio system where we have to actually calculate in the loss, the length of the cable is also going to vary with the signal strength. Because the longer the cable, the less signal we're going to get. So that actually becomes part of the analysis itself. Now, the RF design tool really is very simple to understand. Okay? There are two major areas that go into here. The first one is what we call the data entry keyboard. And that's going to be where we enter in the information on the system itself. Everything within the common elements between the 2 points, such as the frequency, the distance, the name of the project, and the radio that we've selected, are all going to happen in the center part of that keyboard. Then we enter in the information for each side of that system, both the control room and pump site number 1. And what it will then do is it will then point out what signal it expects between those. Now, the way that it's laid out so the fact that we have entered in all of the different available antennas that we have, but you can use any different measurement within there or any different antenna gain by just entering it into those lines and adjusting the cable length that's necessary. But for our purposes here, we need some starting point. So what we're going to do is we're going to do this analysis based upon the Horizon 2.4 gigahertz radio. So this particular one, we look in our chart and say, we don't really know what antennas we want to use for this link. So let's just go ahead and start with the basic ones. We're going to start with a direct mount antenna, which has a 5 dB gain, but no cable. So we enter in 5 dB on the control room side, and we just leave the feed line length blank. On the pump site number 1, we're going to enter in the lowest gain antenna that we have for there, which is actually a 6 dB antenna. But that 6 dB antenna, if we look here on this chart, we'll see here it actually has a 1 or 12 inches or 1 foot of LMR 195. So we then enter that in, 3 feet, sorry. And we enter that information in. And what it's going to do is it's going to give us 2 different variables. The nice part is that we've color coded these, so they're very simple. The positive values are going to give us a green indicator, and negative values are going to give us a red. So we enter in this information, and the result that we get back is going to be based upon how much fade margin we have. Okay, I keep throwing this term around here. I think it's time let's take a look at what that actually means. A fade margin is a little bit different in a radio world, because what we're actually doing is we're not designing to exact numbers. Okay, we actually need, quite honestly, we need to over design the system. Okay, so the fade margin is the difference between what the signal strength we expect and what the minimum level we need to gain any particular RF link. Okay, so if you think about it, the fade margin is actually going to be controlled by all elements of a radio system. Transmit power, feed line length, gain of the antennas. The receiving end is the same way. The receiving gain, the sensitivity, all of these things. Well, quite honestly, who cares? Why do we even need to worry about this? Because we're putting these radios into an imperfect world. Things are going to change over time. Equipment's going to age, antennas are going to go out of alignment being in the real world, and we're now going to have to start dealing with either man-made noise generated from interference. But some basic rules of the transmitter is that you can expect a certain amount of reliability of the system based upon how much fade margin we have. So for example, if we have 10 dB of fade margin, we can generally expect in a digital transceiver about 10% retries. That means 1 out of every transmission is not going to get through the first time, will automatically be retransmitted. 20% will give you 1%, 30 dB will give you 0.1%. So the more fade margin we have in the system, the more reliable the system can be. So we enter this information then into our first packet. We see here that what we come back with is we actually have both green and red listed on our page here. And as you see on the chart here, if we go here, how much can we expect? The fastest that radio can go with the equipment that we've selected is 21.7 megabits per second on the RF link, which is going to give us an equivalent throughput of 10.9. The reason that we put it that way is that after you strip all the overhead, all the security, everything to it, a comparative, basically copper to wire analysis is generally about a 2-for-1 split. So we want to be able to provide what the actual throughput of the system can be, so that when you're looking at an application that has a very high bandwidth requirement, we're going to give you the real numbers. If you dealt with 21.7, you're actually going to be basically having to remove all that overhead every time. So what this link will give us is about 10.9 megabits per second. Okay, if that's good enough for it, the equipment is great. But to be honest with you, we just selected the first antenna that was available to us. What if, for say, we actually then change a very simple thing? Instead of going from a low gain directional antenna, let's go ahead and move it up to a high gain directional antenna. Let's go ahead and move it all the way up to 19 dB. Okay? What does that actually do for our system? Well, as you see here, what that actually does is it actually changes our actual throughput on the system from 21.7, it pushes it all the way to 57.8 megabits per second, which will give us then a overall maximum throughput as far as the copper comparison to 28.9. So we're actually almost able to triple the throughput on the system by simply changing the gain of the antenna. So now you can kind of see where the development or the adjustment of a radio system at this level of it can make dramatic effects on the overall operation of the system. So this program allows us to actually go through there, and we can do each and every single one of the links within the system. And I'm going to kind of skip forward ahead so that we don't have to go through each one of them. But if we look here, we do the calculations on each one of these links. We actually have 57.8 to pump site 1, about the same to pump site number 2 because the distance is very similar. Up to the water tank, it actually is a little bit slower. That's just simply for the fact that we have to go between two omnidirectional antennas. The last link we're going to take a look at here, because I want to show you what actually happens if we do run into an issue, is if we look from pump site 1 out to the water tank. We then enter that same information into our calculator to give us a height at 740 feet at one side because of the water tank being on a repeater, and 15 feet at the remote side. We've got a good line of sight between those locations. But as you'll notice here, the data rate is up to the 57.8 what we expected before, but now we actually have what's called this Fresnel Zone warning. Okay? What this Fresnel Zone warning tells us is we now have the potential for a problem in the system. What does that actually mean? Well, when we're dealing with higher frequencies, and generally we take this calculation in any frequency above 900 megahertz. Radio waves don't run in straight lines. It's not a perfect straight point-to-point system. What it actually does is it actually broadcasts out, especially looking at a directional antenna, in kind of a large cone. Well, if you were to compare those two cones together, it creates this ellipsoid, or this football shape. If anything comes within the first 60% of the distance of that Fresnel zone, and it's based upon, that length is based upon the frequency, okay, it has the potential to cause a destructive reflection. Not that it necessarily will, but in our design side, we need to make sure we can eliminate all of these possibilities out from the beginning, okay? So what we want to do then is we actually want to then say, okay, we have a potential for Fresnel zone warning. And really what that's coming from is at the distance that we have there, at about 6 miles, what we're finding is the Fresnel zone, 60% is actually 32.4 feet, which is listed down here in the bottom of that chart. So what we need to do is we actually need to increase the height of that remote site from 15 feet up to a minimum of 33 feet. So what that does is that then eliminates the possibility of an issue before we actually run into a problem. These are kind of the key benefits that we get out of this RF design. Okay? Why do we do this? Why do we go through this? Quite honestly, we want people to become confident in the systems that they're designing. So we want to provide you with these tools. This RF design program is available for free download from our website. Okay? We cover it quite more extensively in a longer online training class, which is also on the web page. And to be honest with you, if you've got any questions about how the system is done, you'd like us to run the numbers, review the numbers, that's what we're here to do. We want to become your all-in-one radio stop. Okay? Radio applications, they're not hard, okay? But the time and effort that's put into the design side is what's going to make them reliable. I want to thank you very much for attending this. Our next webinar is actually going to be how to optimize the mesh technology. And that's going to go in August 11th at the same time at 8 o'clock. So hopefully you get a chance to review that and join us for that application. If anybody's got any questions, I'll be happy to answer those now. You can, of course, reach out to me at my email address is just simply my last name, Marske, M-A-R-S-K-E, @esteem.com. You can give us a call, and of course, you're welcome to ask us anytime about what we're going to do in the future. So if we don't have any questions, and it looks like must have done a pretty good job, because we don't have any questions at this time, we'll go ahead and stop it for now. Thank you very much for your attendance, and I really appreciate it.